How's it going, guys? So this is Andrew. This is going to be the last video of this series for MBB, and in this video we're going to go over a PID controller, designing a PID controller. Okay, so let me quickly launch Jupyter. Okay, cool. So we're going to design a PID controller. This is our transfer function we've been given. We're going to be designing GC, and we've been given G. Now the requirements. The reason, there's a specific reason we're going to use a PID, and we get that from the requirements. So the question says the controller needs to be designed for this system to ensure that the step response meets the following specifications. So a maximum overshoot of 5%, a settling time of 1 second with a 2% band, and a 0 steady state error. So this 0 steady state error statement tells us, for a 0 steady state error for a step response, tells us that we need a PID controller. And the reason we know that is because if we go to the formula sheet, we come and have a look at this table here, we can see that our system is a type 0 system. And the reason it's a type 0 is because if we look at the transfer function, it's got no poles at the origin. Poles at the origin occur when you've got a single S outside here, where S equals 0 is going to give the bottom equal to 0, the denominator equal to 0. So we've got none of those, which means it's got a type, we are a type 0 system here. Okay, so type 0 system has a finite error, but the requirement said that we need a 0 error, and therefore we use a PID because we increase the type number by implementing a PID controller. And why is that? That's because if we look at the formula for a PID controller, it multiplies G by this over S, and then there's our pole at the origin, which transforms this into a type 1 system and satisfies our steady state error of a unit, a step input for 0. Okay, cool. So that's why we're using a PID controller. Now, to design the PID controller, we use the, first of all in the code, we're going to define G, which we've done here. Okay, and then to define the controller, we use this formula as we saw in the formula sheet. We use this last one. Now we need to choose a value for Z1 and Z2, and the way we do this is we print the poles of G. So G is this function here, and we print the poles of this function. Okay, so if we print the poles, we can see that -7 is the slowest pole, and if we plot the root locus, that basically means that the slowest pole is the pole closest to the imaginary axis. Okay, cool. So, and we see that that is -7. Okay. There we plotted the root locus, and we just explained the slowest pole. So now our Z1 and Z2 are going to be plus and minus 10% of this value. So if S is 7 is our slowest pole, we're going to have Z1 as -7 minus 7. I mean -7.7 and -6.3. That's plus and minus 10%. It's going to sit on either side of the root locus. So it's going to sit here. It's going to sit there, and it's going to sit there. Those are our two Z values. Cool stuff. Now once we've got the two Z values, we can now define our controller. Note that we're not including KD in this. We're going to find this on the root locus. Okay, so here's defining GC. Okay, and when we print GC, we get this, which is correct because you want to have S is S squared, and then S is just one S, and if we look at the thing, if we look at what the program gives us, it's S squared and S. Cool. So the controller looks relatively correct, and then we multiply G by GC. So what we're doing here is, if you come here, we're multiplying G by GC. Now we're going to plot this open loop transfer function in the root locus and find a K value for it, and that would be this KD value. Okay, so we run this cell, and that gives us that. Here's G times GC. Now we plot the root locus of this open loop transfer function GCG. Okay, let's print it. Cool, so that's the root locus of the open loop transfer function. We've been given a % overshoot requirement of 5%. So with that, we need to find a zeta value. Okay, and a zeta value we find from the formula sheet, and we say % overshoot is 5, so between 0.7 and 0.6, I would say zeta is probably 0.68, I think 0.68 maybe. So let's have a look. Let's choose 0.68 as zeta, and I think I set that up wrong, that's why it looks funny. Okay, so we print that, and that gives us our line over there. Cool. So technically we should choose a value on the root locus lower than this, but we're going to just choose a value here. Okay, and then note that this pops up here, and your k value should be 1.292, and I've done all this in plotting the root locus. Okay, then we choose an S. I eventually chose an S of negative 18.26. Okay, and we go there, and that's our k value, and then we multiply GCG by k, which is the formula, multiply GC times G times K, and that's going to be our complete forward loop transfer function, and we give it feedback here. Now we're going to plot the step response of this whole system. That's why we give it feedback, and we plot the step response, which I've also covered in a previous video, and that's what it looks like. So with different values of k that you choose, you're going to get different graphs, and you just need to play around with it until you get the right thing. I've just chosen a random one. You can see that it meets the settling time requirement and the % overshoot, but it does look funny. So yeah, you could probably get this to come up some more before it reaches here, but this does meet the requirements. So, and that's all for that video. That's the PID controller. Hope this helps. Yeah, cheers.